from SQL to machine learning and graph analysis. Before I start the talk, I want to say a little bit about myself. So I'm a computer scientist who builds systems for data management and data analytics. So the talk is going to be from the perspective of a system builder. And I'm not a healthcare domain expert, but I do have collaborations with IBM Watson Health people, so I'm exposed to healthcare domain data and some of the problems. Okay, so in this talk, I will try to provide a roadmap for big data and help you navigate through the landscape. So the first question before we talk about big data analytics is, what is big data? And the most popular definition of big data is Gartner's 3V definition. So basically there are 3 V's. The first is data volume. Of course, that's the size of the data. The second is data velocity. It's the speed at which data is processed or generated. Then the third one is variety, which means what kind of data types are you supporting. And over the years, people had extended this definition with more V's such as variability, veracity, visualization, and value, and so on. One interesting question people often ask is, how big is big data? So how do you know that you're dealing with big data? Well, it's all relative, and also it's a moving definition because of the advancement of storage and computation technologies. And from the 3V definition, we know it's not all about volume. And there's no agreed upon answer to this question, but my answer for this is, you're dealing with big data when the conventional data management or analytics tools are not enough for you. Then why is big data important for healthcare? Well, on one hand, you have large volume data accumulated in healthcare, driven by e-health, mobile health, and the wide use of sensor and wearable technologies, and also genome sequencing technology. On the other hand, a number of new healthcare applications start to emerge, such as personalized medicine, clinical risk intervention, and predictive analytics. Okay, for big data analytics, different people, big data analytics means very different things to different people. For some people, it's machine learning. For other people, it's data mining. And for others, it may be just SQL analytics. This is not surprising because big data analytics come in different forms. So in this talk, I will try to basically categorize the big data analytics along 2 dimensions. In the first dimension is data types. So you have structured data. These are usually relational records in relational database, tables, and semi-structured data. These are usually XML data or JSON data. And unstructured data is usually text. And then you also have graph data to represent the social network and interactions, and also multimedia data is also very popular in healthcare domain, images and videos. The second dimension is complexity of analytics. So the simplest, analytics is basically data entry and retrieval. An example would be look for a patient's electronic health care record when this person checks in at the hospital. And then the next level is basically descriptive summaries. These are basically try to group data somehow and then provide some statistics on different groups. An example would be compute the number of outbreaks of a disease across different georegions. The next level goes beyond the simple descriptive summaries to actually discover patterns using data mining. An example would be identify unusual patterns for medical claims by clinics, physicians, and so on for fraud detection. The last type is predictive analytics using machine learning. And an example would be to predict a patient's readmission to the hospital based on history data. So here is the landscape for big data analytics using these 2 dimensions. So on the horizontal dimension, you have data types. On the vertical dimension, you have analytics complexities. So I'm not an expert in text or multimedia data, so I'll try to focus on structured, semi-structured, and graph data in this talk. So for structured data, data entry and retrieval is basically online transactional processing, or abbreviated as OLTP. Whereas for semi-structured data, people usually use key value or document stores such as Cassandra or MongoDB for doing data entry or retrieval. Graph data is usually people using graph databases to do data entry and retrieval. For structured and semi-structured data, people use SQL and Hadoop systems to do OLAP or online analytical processing, or abbreviated as OLAP. And for graphs, people compute degree distributions, clustering coefficient distributions, and so on. So for structured and semi-structured data, people use data mining and big data to do frequent pattern mining, anomaly detection, and clustering. And for graphs, there's a big group of researchers working on graph processing systems for doing graph clustering, influence analysis, and so on. And for almost all the types of data, people use machine learning to do predictive analytics. So over the years, I have worked on a number of big data analytics, a number of types of big data analytics, including SQL-on-Hadoop, big data machine learning, and graph analytics. So I'll touch these areas in this talk. So start with the SQL-on-Hadoop systems. Before I talk about SQL-on-Hadoop, I just want to give you a little bit background on traditional SQL processing. There are actually two types of SQL processing: the online transactional processing (OLTP) versus online analytical processing (OLAP). The differences between them are listed in this table. So OLTP is mostly for data entry and retrieval, whereas OLAP is for descriptive statistics. So they are basically mostly for BI and business intelligence reporting. And in terms of the queries, OLTP is just simple, read, insert, update, and delete, whereas OLAP is a little bit more complex and ad hoc. In terms of speed, OLTP has very high speed requirement. It has to be real-time, and the emphasis is on low latency and the throughput. Whereas OLAP, the requirement is a little bit relaxed, but you still need to be interactive. And the database field has evolved into having specialized OLTP systems for transactions and specialized OLAP systems for analytics queries. And they're usually connected by ETL process. ETL stands for extract, transform, and load. And so ETL basically consolidate and transform the data from transactional systems into these analytical systems. And in traditional SQL, OLAP system is usually an enterprise data warehouse. So I sometimes use EDW to represent OLTP OLAP systems. And SQL and Hadoop basically focus on this type of analytics. So why do we still need SQL in big data? Why do we need SQL and Hadoop? Well, because SQL is the basic de facto language for BI and reporting, and many healthcare analysts and hospital IT experts are very familiar with this language, and in fact, many existing applications are built on SQL. So therefore, SQL and Hadoop essentially ease this transition to big data for these applications, because you don't really need to change much, and you're still using SQL, and you can still use your application, still use your BI tools. And also SQL and Hadoop also try to overcome some of the shortcomings of traditional data warehouse, such as scalability, fault tolerance, and better support for semi-structured data, and also the ability to directly work on raw data without having this ETL process. So a lot of the time you can just dump your data on the distributed file system, and you can use these SQL and Hadoop systems to query them. So this is a SQL-on-Hadoop landscape. There are a lot of SQL-on-Hadoop systems these days, and I try to characterize them in three camps. The first camp basically support existing data with open format. Those are the things I said. You can just dump your data in the open format, and then these systems can query on it. The second camp basically try to control the storage system and try to and uses a proprietary format. So for this system, you have to do kind of a load to load your data into these systems, and there's a little bit lock-in here. And the third type of system, they are coming from the traditional data warehouse. They're extending traditional EDWs into querying big data as well. Of course, the vendors are mostly from these traditional database companies. Okay. So the major technical challenge in SQL-on-Hadoop is basically how to distribute data and the computation in a large cluster of machines for performance. And quite often, network becomes the bottleneck for performance. And here I will use a database join operator to illustrate this challenge. So join in database is basically an operator to combine different columns of multiple tables together. In this example, I have a table called clinical visits and another table called patient information. I want to join these two tables on the patient ID, PID. So the join operator basically combines the rows from the first table and the rows from the second table based on this PID. And you get the result like this. Now imagine now you're in this big data setting. All the data are actually partitioned and distributed across the machines in the cluster. And so as you can see, if you want to join the different rows together, you need to basically grab a lot of data from other machines. So there's a lot of network transfer here. And there are a number of strategies these SQL-Hadoop systems apply to basically overcome this challenge. One strategy is storing data in formats that are easy for query processing. For example, a lot of these systems actually use Parquet or ORC files format. Those are basically using column-oriented organization that are very easy for basic scanning, just picking up a few columns of a table instead of actually always have to scan the whole row of all the columns of a table. The second strategy is pushing analytics close to data. For example, a lot of the systems use very intelligent readers to basically apply predicates and projections while you're scanning the data, so you don't need to send these unnecessary data across the network. And another strategy is basically using query optimization in database to carefully choose what algorithm to use and what data to ship across the network based on the data characteristics. In one of my work, I basically studied the different join strategies in big data and try to provide some guidance on how to choose a particular algorithm for a particular operation. As an example, so one popular join strategy is basically when you join a big table and a smaller table, these are all relative. In big data is doing broadcast join. So in here, I have two tables, and the tables are partitioned and distributed across the machines. And here, the green table happens to be the smaller table. So we basically ship all the partitions of the green table to every node, to every machine in the cluster, and do local joins. And the network cost is roughly 2 times of the size of the green table. Well, if you're joining two very big tables, then you want to use a different strategy. Here, you want to repartition the both tables and send the corresponding partitions of the two tables to one of the node and do local joins there. And this is the network cost for that strategy. And as you can see, depends on the size of the table. One strategy may win in a particular situation. And other strategies for SQL-on-Hadoop system include pre-process the data into a better organization for queries. For example, you can pre-partition your data, and if you pre-partition two tables based on the join key the same way, then when you join them, you only need to grab the corresponding partitions together, and this will reduce the network overhead. Other strategies include building auxiliary data structures such as indexing and synopsis for eliminating unnecessary data. Often using better data placement can give you a performance boost. In one of my works, I've worked on extending Hadoop distributed file system to support co-location of data. In this example, if two tables are not only co-partitioned but also co-located, then doing join doesn't really incur any network overhead. So much about SQL and Hadoop. We now move on to machine learning on big data. SQL analytics tools are not really enough to capture the full value of big data. And this is where machine learning comes to help. And machine learning is really not a new field, but it has been revived by big data. On one hand, basically, more training data usually leads to better prediction. It's not always true, but generally true. And also, we have enough data today to actually build a model with billions of parameters. This basically makes deep learning a possibility. But on the other hand, big data also brings in a lot of challenge to machine learning, such as scalability and distributed computing. And moreover, it basically increases the learning curve for data scientists, because they do not need to worry about what machine learning they need to use and write, but also how to parallelize or distribute the computation. So to reduce this learning curve, a number of big machine learning systems have emerged. And they can be categorized into two camps. One camp is for general machine learning, and the other camp specializes in deep learning. And the trend is that currently the trend is that these two camps actually try to converge. With general machine learning system try to introduce deep learning algorithms, whereas the deep learning systems try to also cover the basics machine learning. So I don't have a lot of experience in deep learning, so in this talk I'll focus on the general machine learning systems. So the big data system try to help reduce the learning curve by hiding a lot of the implementation details for machine learning on big data. And there are different levels of abstractions that these big machine learning systems provide. The first group of systems such as Spark MLlib or H2O or IBM Watson, they basically provides a library of machine learning algorithm for you to choose. And each algorithm can be somewhat controlled by setting different parameters into the algorithm, but that's pretty much it. There's usually no way for you to change the internal algorithm. So this problem is addressed by the second group, declarative machine learning. This system usually provides you a kind of R or MATLAB-like a language for you to write your machine learning algorithm. So I've worked on SystemML over the years, and this is how you can write the linear regression with conjugate gradient method in SystemML. As you can see, it's basically using matrix operations and as well as control flow statements to write the algorithm. And these systems also basically apply cost-based optimization, just like in database, to basically compile your algorithm into efficient runtime based on your target platform, whether it's Hadoop, it's Spark, or single node. And this system give you the option of basically writing your own machine learning algorithm, but also they can provide you a library of existing algorithms. So the third The third group is called AutoML. This is a concept proposed very recently by H2O. So it basically, data scientists usually will try a number of candidate models on the data and then selects the best one. And AutoML tries to automate this process. So it's another higher level abstraction provided by machine learning. Okay, so I'll now briefly talk about graph analytic systems. So graphs provide a very powerful primitive for modeling real-time data, real-life data and their relationships. And in healthcare domain, examples are patient-patient and doctor-patient interactions, biological pathways, protein interaction networks, etc. And there are two types of graph analytic systems. One is a graph databases. Graph database, they focus on real-time graph analytics. The other type is graph processing systems. They focus on long-running batch processing of graphs. And popular real-time graph analytics, graph analytics system include GenusGraph, Neo4j, etc. And they besides the update, simple node and edge retrieval, they also often support pattern matching for graphs. So given a graph, you try to find subgraphs in your database that match your query, and the match can be exact or approximate. Most of these existing systems support exact graph matching, but sometimes approximate matching can be important, especially when your data is noisy. So in one of my work and during my PhD, I developed a tool called Saga, which helps you to query, a graph that query a database that approximates the pattern you want to query. An example for this would be query a disease pathway against a database of known pathways to find out what biological processes are affected by a disease. The second type of graph analytics system is graph processing, and they focus on batch graph analytics. So these are usually long-running and often iterative analysis on entire graph. An example would be PageRank to find the influencer. So it requires many iterations and takes a long time to compute. The performance bottleneck in these type of analytics again is the network overhead, and many of the systems try to organize data better, to use better graph partitioning and try to absorb the network message within partition, or actually applying techniques such as combining messages when the message can be actually aggregated. Okay, so I've now talked about different types of big data analytics, but the problem is here, many times, an application often requires different types of analytics together. Example, the SQL and the machine learning are often come hand in hand because SQL is used to actually prepare the data for machine learning. Here I'll just give you an example for application that requires integrated analytics. So Medtronic and IBM Watson Health have a partnership to help improve the life of diabetes patients. What they do is basically gather patients' readings from these insulin pumps and glucose monitors and combine them with other information from the individual activity trackers and diet. And they use pattern recognition from Watson to provide feedback on how a patient can manage their diabetes. So a concrete example, they can basically warn patients of abnormally low blood pressure, low blood sugar level up to 3 hours in advance. So as you can see, this the blue lines usually indicate they're using SQL analytics to prepare the data, and then the red line is basically using a data mining or a machine learning algorithm to do analysis. So there are two solutions for integrated analytics. The first is basically integrating existing analytics systems. So integrate a machine learning system with a SQL system. And here the challenges are basically, one is data transformation, how to transfer the data formats between the systems. The other is how to actually transfer the data from one system to another. The second solution is basically building a system from ground up that support various types of analytics in one system. An example is Spark and also Wildfire. This is the system I'm trying to build, and a prototype, a beta release is called IBM Project Event Store. So here we basically integrate our proprietary technology with Spark, and we support basic OLAP processing, OLTP processing, graph, the graph database on the sort of real-time graph analysis, as well as batch graph processing and the machine learning and streaming, etc. So to kind of conclude, so the first takeaway message I want you to get is big data analytics come in different forms. And when you choose an analytics system, you need to ask these questions. What type of data do you have? What level of complexity does the analytics require? What is the latency requirement? And the second message I want you to take is often an application requires different types of analytics together, and this is basically a requirement for integrated analytics. And there, the questions you need to ask is, what types of analytics do you need to integrate? What is your performance requirement? And do you have to basically integrate existing analytics pipelines together due to legacy reasons, or can you actually start with a system that supports various kinds of analytics? I still have some time. I want to briefly give an overview of IBM Watson Health. So as I said, I'm really not a healthcare domain expert. These slides are borrowed from my colleagues in Watson Healthcare. So these are the 5 basic domains IBM Watson Health cover: government, value-based care, imaging, life sciences, and oncology and genomics. And to just give you one example how big data is used in IBM Watson Health, this is IBM Explorer's offerings for life sciences. So it basically integrating all different kinds of a variety of different data format, different data sources together, and doing data integration, cleaning, and etc., and put it in the data lake. And then they support basically 2 type of application or two groups of application for for basically hospital personnel and etc. They identify the data, they do person matching and support index and search. And on the other hand, for life scientists, they usually anonymize the data and de-identify the data. And the services they provide is help you to search and index data and etc. So that's basically an overview of IBM Explorer's offering. That's the end of my talk.